So for this section, we're going to be talking about linear inequalities. So a linear inequality is basically a way of solving a new type of equation. They aren't technically equations, but they work very similarly, which we'll actually talk about in this process. So to solve a linear inequality, we treat it the same way as an equality. So we treat it the same way as an equal sign. But dividing and multiplying by a negative now flips the inequality. So if you had a greater than symbol, something that looks like this general shape, then you would flip it to a less than symbol, like this, whenever you multiply or divide by a negative number. From there, a note that we have: when giving answers in graphs and intervals, which is how you give your answers when you're dealing with linear inequalities, if the problem starts with a less than or greater than symbol without an equal sign underneath it, then your answer will contain parentheses. But if it contains that equal sign with the less than or greater than symbol, so less than or equal to or greater than or equal to, then your answer will contain brackets. This means that the value that you are less than or greater than or equal to is contained, and this means the value is not contained. So for example, we have 5x minus 1 is less than 9. We want to go ahead and graph this as well as solve for the interval. So the first thing we want to do, just like with an equation, we're going to add 1 to each side, which gives us 5x is less than 10. And then we will divide each side by 5 to get the x alone, which gives us x is less than 2. We didn't flip the inequality because we didn't divide or multiply by a negative number. So x is less than 2 represents all of the answers to this original inequality, every number less than 2. So if we were to graph that, we would set up 2 and then just show a number to the left and right of it, so 1 and 3. And how do we graph every number that's less than 2? Well, we set up a parenthesis at 2, because we're not containing 2, we do not put a bracket. So the parenthesis says not 2, but we now shade to the left of 2 and put a second arrow. And this tells us every number that is to the left of 2, not including 2, will solve this problem. And now the interval notation comes directly from this. We have a parenthesis at 2, and we're going all the way to the left. What's the leftmost number that you can think of? Well, every number you can think of to the left of 2, there's going to be another number to the left of it, which means it's going to go all the way to negative infinity. And whenever you're dealing with infinity, whether it's positive or negative, you put a parenthesis because you can never reach infinity. Just like you can't reach this 2, it's not included, infinity is not included. You can never say this exact number is infinity. So this gives us our graph and the interval notation. From here, the next type of inequalities that we deal with are compound and inequalities. So a compound and inequality, to process that, to go through the problems that is, the first thing we have to do is solve each inequality separately. And once we solve each of them separately, we are going to graph them in one number line. We will graph them together. And with a compound and inequality, whatever commonly shaded area you have, that represents the answer to the entire problem. So what does a compound and inequality look like? Well, we say if you have something like if you have something like x minus 3 is less than 5 and 2x plus 4 is less than 14. So both of these statements are happening at the same time, and they both must be true at the same time because of that and. So let's go ahead and solve these. The first one, we'll just add 3 to each side to get x is less than 8. The second one, we'll subtract 4 from each side to get 2x is less than 10, and then divide each side by 2 to get x is less than 5. So in other words, from the beginning of this problem, we now know that these two statements are saying x has to be less than 8 and x has to be less than 5 at the same time. So we'll go to graphing this. We need to contain all the numbers around 5 and 8. So we'll go 4, 5, 6, 7, 8, and 9. To graph x is less than 8, we need a parenthesis because there isn't an equal sign. Add 8, and it's less than 8, so it's going to the left. The parenthesis is opening to the left, and we'll shade. And we put our second arrow. Now we have x is less than 5. So we go to x equals 5. Because it's less than it, again, the parenthesis opens to the left. We shade again, and we put another arrow pointing left. So looking at this problem, what is the common shaded area in this entire thing? Well, the green shading is happening all to the left here, but the red shading only starts up at 5. So we don't include any of these numbers between 5 and 8. And we don't include 5 itself because there's a parenthesis there. To include 5, we would need a bracket there. We have green shading, but only a red parenthesis. So 5 isn't included in both shaded areas. So that means we're going to put a parenthesis at 5. And both of these shaded areas go all the way to the left, so they go all the way to negative infinity. So negative infinity to 5 solves both of these original inequalities. Okay, I want you to take a moment. Go ahead and try to solve this problem. 2x minus 5 is less than or equal to 3, and x plus 2 is greater than 3. Pause the video, see if you can't find this answer. Okay, so let's try this together. Oh, sorry. So, the first thing that we should do here is add 5 to each side, which gives us 2x is less than or equal to 8. And then we'll divide each side by 2 to get x is less than or equal to 4. And now over here, I'm going to go ahead and switch markers. We want to subtract 2 from each side to get x is greater than 1. So x is less than or equal to 4, but x is also greater than 1. So if we start graphing this, we need all the numbers around 1 and 4, so we'll put 0, 1, 2, 3, 4, and 5. And from here we have x is less than or equal to 4, so at 4 there's going to be a bracket, and it's going to point to the left because it's less than, and we put another arrow. And now from there, we have x is greater than 1. That means we have a parenthesis because there's no equal sign. So at 1, we put a parenthesis, and we shade to the right. And now what's the commonly shaded area here? Well, starting at the left side, we have common shaded area at 1, but there's a parenthesis, so we put a parenthesis at 1. And now we go to the right until the common shaded area stops. That's at 4. And at 4, we have shaded green and a red bracket. That means it's contained in both of the inequalities, so we can put a bracket with 4. So every value between 1 and 4, except for 1, solves both of these original inequalities. At this point, we have another type of inequality that is another way of writing these and inequalities that comes up. Sometimes you can combine, you can condense the two and inequalities into one inequality with two inequality symbols. And it allows you to solve them at the same time. So, for instance, if we wanted to solve for y in this case, we would have to get rid of the 4. We'd have to add 4. But because we have two inequalities, we're going to add that 4 to both sides of the inequalities. Everything we do to the middle, we will do to the right and left at the same time. So when we do this, negative 2 plus 4 gives us 2. That's less than or equal to 2y, which is less than 6 plus 4 is 10. And now from here, we'll divide each side by 2 to get 1 is less than or equal to y, which is less than 5. The nice thing about these types of inequalities is the answer is already set up for us. If we were to graph this, we don't have to do two separate graphs. It's just one graph. We need every number around 1 and 5. So 0, 1, 2, 3, 4, 5, 6. And we know that the graph has to be greater than or equal to 1. So we put a bracket at 1. We know that it has to be less than 5. We put a parenthesis at 5. And we shade in between. And the graph looks exactly like the interval. A bracket at 1, comma, a parenthesis at 5. And that's it. Every number between 1 and 5, except for 5, solves this original compound inequality. Continuing on, we now have OR inequalities. To solve an OR inequality, you will again solve each separately and again graph them together. But from there, we say that any shaded area is the answer. So if you can find any part of the graph that's shaded, it is included in your final answer. Because we're saying if this is true or this is true. Any x value that satisfies either inequality counts as the answer. So, going through this, we're going to go ahead and add 3 to each side to start getting x alone. That gives us 2x is less than 10. And then dividing each side by 2, we get x is less than 5. For this right problem, I'm going to go ahead and switch markers again. To solve for x here, we will subtract 35, that is, from each side to get negative 4x is less than or equal to negative 32. And then divide each side by negative 4 to get x and 8. And think about what's going to go in between them. We just divided by a negative number, so we have to flip the inequality. So x has to be greater than or equal to 8. So with that, we'll go ahead and graph these together. We need a number line that contains everything around 5 and 8. So we'll put 4, 5, 6, 7, 8, 9. First, we have x is less than 5. So we want a parenthesis at 5, opening to the left, because everything to the left will be shaded. And now x is greater than or equal to 8, means we want a bracket at 8, and we are shading to the right, because we want everything to the right of 8, everything greater than 8. And now, what does this look like in an interval? Well, we have every number to the left of 5, not including 5, included in our solution. So that means from negative infinity all the way to 5, parenthesis. And we also have every number to the right of 8, including 8 because of the bracket. So 8, bracket, all the way to positive infinity, parenthesis. But how do we say that our answer is both of these things? Well, we have a symbol which we call the union with this capital U. This means the union of these two sets, meaning either one of them counts as our answer. So this entire double interval represents every answer that solves the original problem. Okay, from here, we're now going to talk about absolute values. So we say if the absolute value of u is equal to c, so if the absolute value of u is equal to some constant number, then u is equal to c or u is equal to negative c. Think about why that's true. If you took the absolute value of c, you would get c. If you took the absolute value of negative c, you would still get c. So we have to solve an absolute value, we have to set both of these equations up and solve. Meaning to solve 2x minus 3 equals 11, we will set up 2x minus 3 equals 11 and 2x minus 3 equals negative 11 and solve. But we do have to note that you must check your answers to make sure there aren't any problems that come up with the answers. So, solving this, we will add 3 to each side, which gives us 2x equals 14. And then divide each side by 2 to get x equals 7. And over here, again, we will add 3 to each side, to get 2x equals negative 8. And then divide each side by 2 to get x equals negative 4. And now we'll just do a quick check to make sure this worked out. We have the absolute value of 2 times x, we'll say is 7, minus 3. We want to check if that's equal to 11. Well, the absolute value of 2 times 7 minus 3 gives us the absolute value of 14 minus 3. 14 minus 3 is 11, so we have the absolute value of 11. Is that equal to 11? Yes, it checks out. Over here, we'll do the same thing. The absolute value of 2 times x is negative 4, minus 3. Again, we want to see if that's equal to 11. 2 times negative 4 gives us negative 8 minus 3. Negative 8 minus 3 gives us negative 11. And the absolute value of negative 11 is 11, so that also checks out, meaning both of these answers are correct. X equals negative 4 and 7. Okay, so from there, we'll try another type of absolute value problem that comes up. This statement that we said where u equals c and u equals negative c also works if we're dealing with algebraic expressions, meaning u equals the absolute value, the absolute value of u equals the absolute value of v, where v is not just a constant, can then be rewritten as u equals v or u equals negative v. Just like we did before, except v could be something like 2x minus 5. But note, when you do this, again, you do need to check. So, as I said, it's going to work out just the same as the last problem, except we now have x's instead of constants. So go ahead and take a moment, pause the video, see if you can't solve this problem. Alright, so trying this together, our first statement says remove the absolute values, 3x minus 1 and x plus 5, and set them equal to each other. The second statement says remove the absolute values again, but this time make the right side negative. Now we solve both of these equations and then check. So for the left one, we're going to go ahead and subtract x from each side, which gives us 2x minus 1 equals 5. We'll then add 1 to each side to get 2x equals 6. And then divide each side by 2 to get x equals 3. Over here, though, we have to distribute this negative first, which gives us 3x minus 1 equals negative x minus 5. And then to solve from here, we're going to add x to each side, which gives us 4x minus 1 equals negative 5. We'll then add 1 to each side to give us 4x equals negative 4. And dividing each side by 4, we get x equals negative 1. But remember, we do have to check these. So checking x equals 3, we have the absolute value of 3x minus 1, so the absolute value of 3 times 3 minus 1. We want to see if that's equal to the absolute value of x plus 5, so the absolute value of 3 plus 5. 3 times 3 is 9, so the absolute value of 9 minus 1, we want to check if that's equal to the absolute value of 3 plus 5 is 8. And yes, this checks out. The absolute value of 9 minus 1 is the absolute value of 8. So x equals 3 is one of our answers. And now from here, we check x equals negative 1. So we have the absolute value of 3 times x is negative 1 minus 1. And we want to check if that's equal to the absolute value of x plus 5. So negative 1 plus 5. 3 times negative 1 gives us negative 3 minus 1. And we want to see if that's equal to negative 1 plus 5 is 4. Negative 3 minus 1 is negative 4. So we have the absolute value of negative 4. We want to see if that's equal to the absolute value of 4, which is 4. And yes, that does check out. The absolute value of negative 4 is 4. So both of our answers are correct. X equals negative 1 and x equals 3.